Good day, class. My name is Mojid, and for today's live session, we'll be looking at the subject chemistry. Now, this would be another subject within our long-ranging Jamb class. Now, for today, we'll be beginning with the very basics and looking at all the relevant topics we will have to conquer as far as chemistry is concerned. We will be looking at the concept of chemistry itself, the separation of mixtures, the concept of compounds, that is, elements, compounds, and mixtures. We will then be looking at constituents of air, water, and the likes. For now, let's first and foremost familiarize ourselves with the very beginning and basis for chemistry. Now, when we talk about chemistry, the basics for this is we are interested in the study of how compounds, elements, or mixtures interact. Now, we consider elements as the official standard form in which an individual constituent in chemistry should occur. Now, for elements, of course, we realize that for each element, we have them in their atomic forms. And for each atom, we can bring out the concepts of the proton, the neutron, and the electron. Of course, all of these still have very big similarities. In fact, you'd find out that for the proton and neutron, you'd find them in the nucleus of an atom, and then the electron orbits around that nucleus of an atom. In fact, as we continue further, you'd find out that the atom is in fact the smallest indivisible form of an element. Of course, that is by postulation of one of our chemists. We will now see whatever modifications have been made to that definition of an atom being the smallest indivisible part of an element and the formation of the proton, neutron, and electron inside that atom. This is where we are going to be moving towards. And then once we get here, we'll now move beyond that into balancing chemical equations, as well as looking at various ways in which elements can be combined. We can combine elements to form molecules, we can combine elements to form what we call compounds. We will look at what these terms and concepts mean in detail. But for now, let's break it down step by step. First off, let us consider the element in detail, right? Now, we have said that the element is that individual constituent that forms the basis for what chemistry stands for. Now, for this element that we have, there are some numbers, there are some values that are attributed to this element as a factor. Now, for this element, we will consider the term oxidation number, the term valency, as well as the concept form of what we term as radicals. Now, we'll see how these concepts are interrelated, as well as how easy it is for us to identify these concepts in terms of elements and their forms. Now, first and foremost, let's start with what the valency is. Now, the valency is simply the combining power of any element. In fact, when we say valency, we are talking about the valence electron, which means electrons that are liable to enter a reaction. That is what it means when we talk about valency. Now, do not forget that we have said that the atom consists of the proton, the neutron, and the electron. And that, for instance, if this is the circumference and then we have the nucleus here, and then around this point we have the proton and the neutron, and then we have the electrons orbiting the nucleus of the atom. It means that the electron stays at the edge and is the closest or the farthest, as the case might be. It is the closest to getting that element into a reaction, and it is the farthest away from the nucleus, right? This makes the electron take very big prominence in terms of the element and how it reacts. In fact, we call the valency as the combining power of an element. The combining power of an element. Put simply, this means that for that element, how liable is it for it to combine or react with another element? That is what the valency stands for. Now, of course, we can give a count to that number. We can give a count to that power, that combining power. How then can we make use of it? How then do we realize if that element is in the position of the donor or is in the position of the acceptor? Now, whenever a chemical reaction takes place, we find out that each element either exists as a donor or as an acceptor, or in rare cases or in some cases as a sharer of electrons. Now, if you're a donor, it means that you would have positively charged electrons. If you're an acceptor, that means you would have negatively charged valence electrons. In fact, the moment your electrons become charged, then you would say that the element has become an ion, right? So we say that an ion is simply a charged element. And depending on the charge on the electron, we can either say it's a positively charged ion or a negatively charged ion. When we say it's a positively charged ion, this means that we are saying it's a cation. And then when we say it's a negatively charged ion, then we are simply saying it's an anion, right? So cations are positively charged ions, anions are negatively charged ions. It is important for an element to be charged up in order to carry out reactions. We will get to look at the different classifications of elements in terms of the charge and in terms of their liability to carry charges. First off, let us deal with how the valency works. Now, we have said that if the valency is the combining power of an element, we have to determine the position of that element, either as a donor or as an acceptor. And for that, we would need the charge on the electron, right? This leads us to the concept of the oxidation number. The oxidation number is simply the charge the element appears to have. If the combining power of that element is the valency, then the charge that combining power has is the oxidation number. And we have a lot of examples for this. In fact, you'd find out that we would say, for instance, we will normally say that the element sodium, which is having one valence electron, which means that the valency for sodium is 1, will have the oxidation number, right, of 1. Now, what will now be the charge on that oxidation number? It will be a +1. Now, the question now arises, how then do I know the charge it will appear to have? How then can I determine that charge it will appear to have? And there's a simple rule of thumb that guides this. In chemistry, the biggest, most important foundation is the concept of the periodic table. We will look at it in depth within this Jamb class. Now, what is the periodic table staying for? The periodic table serves to classify the elements based on their properties, based on their characteristics, based on their prominent properties. Now, in fact, the most popular members of that periodic table is what we term as the first 20 elements. And then, of course, they are so common that we know them offhand from our elementary. Let's list them out. We have the hydrogen, so I'll be listing them in terms of their symbols. We have the hydrogen as the first element. We have the helium. We have lithium. we have beryllium, we have boron, we have carbon, nitrogen, oxygen, fluorine, neon. That's 10. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. These are our first 20 elements. We can also write them in full to help our retention. We have H for hydrogen, He for helium, Li for lithium, Be for beryllium, B for boron, C for carbon, N for nitrogen, O for oxygen, F for fluorine, and E for neon, Na for sodium, magnesium, aluminium, Si for silicon, P for phosphorus, S for sulfur, Cl for chlorine, Ar for argon, K for potassium, and Ca for calcium. So these are our first 20 elements that occur as, of course, the first 20 elements within the periodic table. Now, with these elements, we can classify the elements within the periodic table with 3 distinct properties. We classify them as either metals, so classifications of elements, we classify them as either metals, metalloids, or as non-metals. Of course, these elements that fall into these characteristics have different properties. For instance, the metals are great conductors of electricity. They also occur most times in their solid forms. But most importantly, in terms of the valency and oxidation number that we are trying to learn now, the most important concept in terms of the metals is the fact that their oxidation number is usually positive. The oxidation number for metals is usually positive. We can also classify metals in terms of the groups they fall in the periodic table. For the periodic table, it is arranged in such a way that we have what we call the groups and the periods. The groups and the periods. They are arranged in rows and in columns, groups and periods. The groups come down as columns, then the periods go as rows. This is the arrangement in the periodic table, which we will get to in detail. But for now, the most important arrangement or the most important property for elements that we can call metals is in fact the fact that their oxidation number is positive. And sodium, which we picked, is in fact, of course, first and foremost, sodium is the 11th element on the periodic table. It is also in fact a metal. And then the valence electron it has in the outermost shell, because of course we have said that the electron is the farthest member of the atom from the nucleus. Of course, in the nucleus you have the proton and the neutron, and then the electron is the farthest away. So that valence electron that sodium has is just 1. So the combining power of sodium is 1. Now, what condition will sodium be when a reaction takes place? Sodium will take the position of a donor. Remember, we have said that the donors will always have a positive charge in its oxidation number. In fact, it means that sodium, when it is charged up, becomes a cation of course, meaning that it becomes a donor because it is a metal. Now, what happens if we have a non-metal? If we have a non-metal, do not forget that there are different classes of non-metals. Non-metals in essence simply mean elements that are bad conductors of electricity. They rarely occur as metals. They are usually in the liquid state or in fact in the gaseous state. Most of the time in the gaseous state. So they are bad conductors of electricity. And most importantly, the oxidation number is negative most times. The oxidation number is negative. Now, how then can we write out a member of the non-metals? Let's take an example. Let us take chlorine. Chlorine is the 17th element on the periodic table. It has a total number of valence electrons of 7. It has a total valence electron of 7, and by virtue of that, it means that the oxidation number can be expressed as, now, the question now is, will I write this as -7? That is the very first question we'll have to tackle. Now, with the emergence of chlorine, let us now shed more light on how these elements are combined. Remember that we have said that we classify elements into metals, metalloids, non-metals, but that's not even the case that we are going to. The most important part is, remember that we have said that all these elements are arranged within the periodic table. Now, in the periodic table, there is a particular arrangement in the periodic table that draws our attention and help us in figuring out how to write the oxidation number of an element like this. Now, in the periodic table, so first off, let me take this off so we know we are coming back to answer that. In the periodic table, we have that, remember we have said that on the horizontal rows, of course, we are going to look at the periodic table in detail and the various properties each group or each period will have. In this periodic table, we have the groups coming down as vertical rows. Now, let's make a brief preview of what the periodic table stands for. Now, in the periodic table, colloquially, we term that groups 1, 2, and 3 are usually the metal groups. Groups 1, 2, and 3 are the metal groups. What does this mean? It means that elements that fall into groups 1, groups 2, and groups 3 will be termed as metals. It goes further than that. In fact, it means that elements that will have the total number of valence electrons to be either 1, 2, or 3 are essentially usually metals. Example of that is the sodium. So sodium is essentially a metal. Of course, it has 1 valence electron, which means that sodium will fall inside this first group. If you have by your side the periodic table, you can confirm the position of sodium and you'll see that it actually falls in group 1. Now that we have noted that, what about chlorine? Of course, in general, we have 8 groups in the periodic table. 8 groups. Now, let's go to the other side. On the other side, of course, we have, so we are going to start from right to left. This is left to right, right to left. Let's say we have group 8, 7, 6, 5, 4, and so on and so on. Now, in fact, this last group, which is group 8, is also sometimes known as group 0. Why do we call it that? In fact, the group 8 elements have a general name we call them. We call them inert gases. Or we call them noble gases. Elements in group 8 are called noble gases. What does that mean? It means elements that have a total number of 8 valence electrons in their outer shell, which means in their shell that is farthest away from the nucleus, right? They are called noble gases. Now, of course, We have said that noble gases are elements that will have 8 in the outermost shell, but there is one condition, or there is one exception, let's put it like that. There is one element in that group 8 that does not have 8 elements or 8 electrons in the outermost shell. It actually has 2 electrons. However, it is noble. And that element is what we know as the helium element. Helium exactly has 2 valence electrons, and it still falls in the noble gas. Why? In chemistry, whenever chemical reactions occur, there is a simple goal that those elements are trying to achieve. And the simplest goal the elements are trying to achieve whenever they go into reaction is to attain nobility. Look at it this way. In your normal life, you have yourself as a middle-class citizen. Of course, you are always striving to become the boss. You're in a company, you're always having to get so high that you can either become the chief executive or the CEO. If you are in politics, you are entering as the councillor, you are looking towards becoming the president, you are looking towards becoming the Senate president, you are looking towards becoming the apex in your field. Similarly, that same reaction happens for elements as well. The elements, whenever they go into reactions, go with one single aim: to strive to always become noble, become complete, become stable. One of the most important properties of this group 8 elements is their stability. They have absolutely no need to go into reactions. For instance, your president that is already on a second term has absolutely no need to go into an election anymore, because in Nigeria, if you are already running on a second term ticket as a president, you cannot run for a third term, which means that at that point in time, you have achieved the apex. You are at nobility. You are at stability to that extent. So it has no reason, absolutely no reason, to run for the election anymore. This is exactly the same thing that happens with the noble gases. They have absolutely no reason to go into reactions because they are already attained the position of stability because of 8 valence electrons. However, for these ones that have not attained that number of electrons, they must always strive to achieve that. Using that explanation, let us now quickly look at what this will translate in for the oxidation number. For sodium, that is a group 1 element because it has 1 valence electron. Remember that if it is attaining the stable number of 8, the problem gives up a lot of aspects. First off, you having just 1 valence electron, it is almost impossible for you to be able to find another element that will be willing to give you 7 elements or to give you 7 electrons so that you will be complete 8 in your outer structure. This is the position of the sodium element. We can go forward to look at this diagrammatically in what we call the orbital configuration. Let's simply draw the orbital configuration for sodium. Of course, do not forget that all these terms their periods will be looked at in detail. But first and foremost, let us try to understand what the element stands for. Now, the sodium element is of number 11. The orbital configuration for sodium is 2, 8, 1. Now, look at this closely. If you look at these 2 shells, you have 2 on the first shell. In fact, the first shell of any element can only take a maximum number of 2 electrons. Why is this so? This is so that the exception in the noble gas group can be tolerated or can be accommodated. Remember that we have said that helium is the only member of the noble gas group that actually has 2 valence electrons but has still attained stability. The reasoning is simple. Because of the fact that helium exists as a noble gas, we permit that and we use that as our sense of guidance to always make sure that our first orbital or our first shell is always going to attain a maximum of 2. In advanced classes, you will find out that